Hello. Today's lesson is on section 22.1, Conditional Probability. Go ahead and open your textbook to page 1137 in your geometry textbook. And on page 1137, we see the definition for conditional probability. Conditional probability is finding the probability that something occurs given that something else has already occurred. And so the notation, the way we say this, P of A slash B, we say the probability of A given B. And so that's how you say the vertical bar that's there. You just say the word given. So probability of A given B. So that's telling us that we know B occurred. What's the probability that A also occurs? And so if we look at this example of including data of who took medicine and didn't take medicine, and how many headaches occurred and how many patients didn't have headaches. If we say that A is the event that the participant did not get a headache, okay, so did not get a headache, no headache, and let B be the event that the participant took the medicine. So that's this column. And so to find the probability that, what is the probability that a participant who took the medicine did not get a headache? So how many participants took the medicine? And so that is 65. Of these, which ones did not get a headache? And that is 54. And so the probability of A given B, the probability that they did not get a headache given that they took the medicine, is 54 out of 65, which would be about 83%. So you go ahead and try part B. This time we're looking for the probability of B given A. So see if you can fill in the blanks there to calculate what is the probability that somebody took medicine given that they did not get a headache. So we have participants that did not get a headache. There were 76. Of these, 54 took the medicine. And so the probability of B given A, 54 out of the 76. And that is about 71%. And then for part C, let N of A be the number of participants who did not get a headache, N of B be the number of participants who took the medicine. We have N of A, we said, is 76. N of B, we said, is 65. The intersection of the two is 54. And so writing probability of A given B as a quotient, we have, for this one, we said it was, when we did up here, we said it was 54 over 65. So that is the number of elements in A intersect B. Because, see, we used the 54 on top, and that's A intersect B, and then we divided by 65 in the bottom. That was N of B. And then for the second example,
Hello, Mr. Dixon.
So to calculate the probability of B given A, we did 54 divided by 76. 54, again, was the intersection, A intersect B, and the 76 that's in the bottom is N of A. So based on what we did in this problem, we can see that the probability of a conditional probability can always be calculated as the intersection over the probability of the second letter, or what was given. And so that is expressed on, let's see, on page 1139. So this is in general how you can calculate a conditional probability, by doing the intersection on top divided by the probability of the given that attribute in the bottom. So probability of A given B is always going to be the probability that both A and B occur divided by the probability that B occurs. So this formula is useful. We can use it for any of these conditional probability problems, but you can also find that many of the problems that we do, you don't really need to refer to the formula if you just think about the isolated group that you're looking at. So let's see how we can do this next example. We'll do it two different ways. We'll do it once with the formula and once without. So let's see. So we have a standard deck of playing cards. Find the probability that a red card randomly drawn from the deck is a jack. So we're trying to find the probability that we get a jack given that it is red. And so to do this without the formula, you would say, okay, we already know it's a red card. It's given that it's red. There's only 26 red cards in the deck. And how many jacks are there in the red cards? Well, there's a jack of diamonds and there's a jack of hearts. Those are the only red jacks. So there's going to be two red jacks, or two jacks out of the 26 red cards that we have. So that is 1/13. So I didn't use the formula at all. I just said, we know that it's red, so that narrows the deck down to 26 cards. The probability of getting a jack when we're looking at only the red cards is 1/13. So now here's how you would use the formula. So the probability of getting a jack given that it's a red card is the probability of a jack and red divided by the probability of red. That's based on the formula up here. So the probability of getting a jack that is also red, there are 2 out of the 52 cards in the deck. The probability of getting a red card, there are 26 red cards out of the deck of 52. And so if we write that as 2 over 52 times the reciprocal, 52 over 26, the 52s cancel, we get 2 over 26, which is also 1/13. So we get the same answer in both cases. The probability of jack given red is 1/13. And that matches the same thing that the publisher worked through in the example here on the bottom of 139 and going on to 140. They got 1/13 by doing the same quotient that we did using the formula. So my point is, you don't have to use the formula. Most of the time you'll have just as much success without using the formula, but just know that the formula is there. So if you come across a problem that is a little confusing or challenging, you can try doing it without the formula, and then you can also try doing it with the formula and see if you get the same result. So let's go ahead now and try example B. So press pause on your player. See if you can fill in all the blanks for example B. That's using the formula. In their example, they're using the formula all the way through. So what you might want to do is try just over on the side here, try doing this problem over here on the side without the formula, see what you get, and then work through filling in the blanks in the text and see if you get the same answer using the formula. Okay, so go ahead and press pause, and then after you're done completing all 4 steps here for example B, press play and see how you did. So this time we're looking for the probability that we have a that a jack randomly drawn from the deck is a red card, and so this time we're looking for the probability that it's red given that it is a jack. And so we know there are 4 jacks in a deck of 52 cards, so the probability of a jack is 4 out of 52. The probability of jack and red, we said that there are 2 red jacks in a deck of 52. And so then filling in the formula is the intersection we said is 2 out of 52. Probability of jack is 4 out of 52. And so then if we do 2 out of 52 divided by 4 out of 52, we can multiply the top and the bottom both by 52 over 52 and get 2 over 4, or 1/2. Now that's using the formula, so let's see, you might have done it first without the formula, as I suggested. So here we know it's given that it's a jack, so now we're only looking at the 4 cards in the deck. So that makes it a lot easier, because as soon as it's given that it's a jack, we throw the rest of the deck out. We're only looking at the jacks, and so out of the 4 jacks, what's the probability that it's red? Well, out of the 4 jacks, 2 of them are red and 2 of them are black. So the probability of drawing a red one is 2 out of 4. And so that problem is actually maybe simpler to do without the formula, as is true for many of the problems you're going to do. So again, the formula is optional if you know how to do these without using the formula, just like I reasoned through here. What we're doing is we're isolating what we already know, and that eliminates, in this case, eliminates a lot of cards that we need to consider. So go ahead and this time try the Your Turn problem 5 and problem 6. So press pause on your player, and then when you're done with both problems 5 and 6, then press play and see how you did. Okay, so for problem 5, we're trying to calculate the probability that we get a king given that it's a face card. So king given face card. And so if it's given that it's a face card, we know that there are only 12 face cards in the deck. We've got jacks, queens, and kings, and so there are 4 of each. So as soon as we know it's a face card, we know that we're only dealing with 12 cards now, because there are 12 face cards in the deck. So how many of those are kings? Well, 4 of them are kings out of the 12 face cards. So that is a probability of 1/3. So again, that answer came pretty easily without using any formulas or anything like that. But if you wanted to use the formula, you'd say probability of king given face card is the probability of a king and face card over the probability of face card. And so that would look like this. The probability of a card being a king and a face card, there are 4 of those in the deck of 52. And the probability of face card, there are 12 in the deck of 52. And so then if you flip the denominator and multiply, the 52s cancel, you get 4 over 12, which again reduces to 1/3. So we get the same answer, 1/3, in both cases. For problem 6, this time we're finding the probability that a queen randomly drawn from the deck is a diamond. So we're looking for the probability of we're looking for the probability of diamond given queen. Probability of diamond given queen. So if we know it's a queen, we've already reduced our number of cards to 4. So we know it's a queen. There's only 4 queens in the deck. And what's the probability that it's a diamond? Well, there's only 1 diamond out of the 4 queens in the deck. So the probability is 1/4. That's without using the formula. If you want to use the formula, probability of diamond given queen is the probability of diamond and queen divided by the probability of queen. And the probability of diamond and queen, there is 1 queen of diamonds out of 52. And the probability that it's a queen, there are 4 queens out of 52. And so then we get 1/4. Same answer. And so that's it for today's lesson. Pretty short lesson. If you try some of the exercises and get stuck, you can always come back and watch parts of this video again if you need to.